Okay, so what we're going to look at now are simple harmonic oscillators, because it was requested to do a couple examples, so let's take a look at them. So first, let's start about where it comes from. It comes from Newton's law, which is just F equals ma. And in this case, we just have a spring right here with a mass attached to it, and you're going to displace it from the equilibrium point. And from Hooke's law, we know that the force is negative kx, and that equals mass times acceleration, which is the second derivative position. So we need a formula whose second derivative is equal to its negative of its first, or what it originally was. So what's a function that does this? Now if you think about it, sines and cosines do this. So what we are going to do is we are going to make a function. This would be our position function. Take the derivative of it, you get negative, you get velocity, take the derivative again, you get negative a omega squared, so just some constant. But this a cosine omega t, that looks exactly like our first function. So that's the one we're going to use. And we're going to pick cosine because we're going to start pulling away. And cosine starts at 1 or negative 1, depending on where you are. So that's what we're going to use. So we plug this in here, and we can see, oh look, negative. This is my function for x, a cosine omega t plus phi. And that equals over here. So the parts in yellow are going to cancel out. And the angular frequency, which is how fast your cosine function is going to change, is going to be equal to the square root of k over m. Or right here I have it written as omega squared is k, the spring constant, divided by the mass. So if you have a bigger mass, it'll oscillate slower. If you have a stiffer spring, it'll oscillate quicker. Now, one note on position, let's kind of talk about this. A is your amplitude, that's how far, so this right here would be equilibrium. This is amplitude, how high it is. And it would drop down, and then it would go back and forth as it displaces. So A is our amplitude, how high we are displaced from equilibrium, like we just mentioned. Omega is angular frequency, that's how fast you go through this function. Faster angular frequency, it goes back and forth quicker. All right. So let's do a quick example. We have a spring that has a half kilogram mass attached to it. The spring is displaced 25 centimeters from equilibrium, completes one oscillation every 10 seconds. So we start with our general equation. There's no offset, so phi is 0. And what's our amplitude? Well, that's maximum displacement. So that's just 25 centimeters or 0.25 meters. Okay, easy enough. You can just read that from the problem. Let's look at omega. Now we don't have omega, we have the period, 10 seconds. Now 10 seconds, that means every 10 seconds it completes one cycle. So if I want cycles per second, that is frequency, so period is 1 over f. So your frequency on this would be 1 divided by 10, or 0.1 cycles per second. Now I want to convert from frequency, cycles per second, to omega, radians per second, angular frequency, because that's what goes in that cosine formula. I know there are 2 pi radians per cycle, frequencies in cycle per second, so omega is 2 pi radians per cycle times 0.1 cycles per second, or 0.628 radians per second, and that gives me my angular. Okay, so now what we're looking at, we want to find k. And if we look at this, we have a spring constant half a kilogram. We know omega squared is k over m, so we solve for k. We get k is equal to m times omega squared, or half a kilogram times 0.6, should be 628 squared. Okay. So let's talk about what we can do with the period of a pendulum. Now, for a simple pendulum, we know that x is just going to be, start out exactly the same way. You need a function that's going to oscillate. Small angle approximation, theta is less than 5 degrees, and you get omega squared as g over l, acceleration due to gravity over l, and you get your period as 2 pi square root of L over G. We found this in lab, so you should have plenty of experience seeing this. What can we do with this? Well, let's say we measure the period of a pendulum to be 9 times what we measure on Earth. What's its acceleration due to gravity in this new world? So we know, starting with Earth, and here's our new world. Now we know a ratio, so let's go ahead and divide these two together. So I take the Earth expression, divide it by my new world expression. And then let's convert. We know that the period in the new world is 9 times period on Earth. Everything in red cancels out, giving you 1/9 times gravitational acceleration on the new world, because it's bottom of the bottom, goes up to the top, divided by gravitational acceleration due to gravity on Earth, square root. So it's 1/81th, 1/81st, why not, times 9.8 meters per second squared. So one of the tricks to know, if you don't know something, you can always set them up as a ratio if you know a relationship between the two. Knowing a relationship between two quantities is just as good as knowing the actual quantity itself. I hope this helps, and let me know if you have any more questions. Thanks.